Hi everyone, and welcome to AP Daily. My name is Tim Gallagher. I'm an AP Computer Science teacher from Winter Springs High School, located just outside of beautiful Orlando, Florida. And today we are going to be continuing topic 3.6. This is equivalent Boolean expressions, and this is the second of two videos. And we're going to talk about truth tables and how we can use them to prove our Boolean identities and evaluate equivalent Boolean expressions. So what will we learn? Well, we're going to continue to compare and contrast our equivalent Boolean expressions. We're going to revisit De Morgan's laws and how they can be applied. We're going to talk specifically about truth tables in this video and use those to prove our Boolean identities and show that equivalent Boolean expressions will always evaluate to the same value in all cases. So what are truth tables? Well, truth tables are a fantastic tool to help us evaluate and show equivalency in Boolean expressions. And by testing all of the different combinations of the Boolean values, the truth table makes it easy to see all the possible outcomes that we'll have. Let's look at an example. So here's a truth table, and what we did here is I have two Boolean values. They could be, again, expressions or variables, but we're going to call them P and Q. And I want to look at all the different combinations of true and false that I could have for both P and Q. So I have a table set up. And I have these values where P and Q are both true. I've got P is true and Q is false. P is false and Q is true. And both of them equal to false. So this is all the different combinations I have. And for this basic truth table, we're going to look at and, or, and not, and just to see what the values are so we can get some practice filling out a truth table. So what is P and Q? Well, when they're both true, we know that P and Q will be true. When one of them is true, well, P and Q is going to be false because remember, and they both have to be true. False and true is going to be false, and if they're both false, P and Q will be false. So these are all of our possible values of P and Q given the different values and combinations for P and Q. What about P or Q? Well, P or Q, when they're both true, that's going to be true. When one of them is true, P or Q will also evaluate to true. But when they're both false, then P or Q will evaluate to false. And then we have our not values. Well, P is true, true, false, false. So what is not P? That's going to be false, false, true, true. And likewise, Q, in these combinations, we have true, false, true, false. So not Q will be false, true, false, true. And that's a truth table. And you can see that none of these columns are the same, so none of these expressions are equivalent Boolean expressions, which we didn't expect them to be. Not doesn't behave the same as or, and or doesn't behave the same as and. But let's look at De Morgan's laws and a truth table here. So I've filled out my P and Q, and I've even brought over the not P and the not Q from the other table. And here are two Boolean expressions that, according to De Morgan's laws, are equivalent. Always. Not P and Q. When I distribute the not and I flip the and to become an or, that becomes not P or not Q. So let's evaluate these. So when P and Q are both true, let's see, P and Q is true, and then not true, that's going to be false. True and false is false, not false is going to be true. False and true is false, and then not false is true. And then finally, false and false is false, not false is true. So there's this expression. Let's evaluate these. So not P or not Q. When we evaluate, if you remember the order of operations for our logical operators, we're going to evaluate the not first, each not first, and then evaluate the or. So not P, not Q, and then look at the or. So not P is, and I have these already, not P is false, or not Q, false. Well, false or false is still going to be false. False or true, again, this is not P or not Q, that's going to be true. True or false, that's going to be true. And then true or true, again, looking at the not P and the not Q, that's also true. Well, what do we notice? If we look at this column and this column, they're the same. That tells us that for every possible combination of P and Q, these two expressions are the same. So we've proven that De Morgan's law is true for all possible values in all cases. And we know that these equivalencies are what we stated in the last video, again, by looking at these columns. So let's practice some of these. Here's a truth table, and I just have some random Boolean expressions. I've got P and Q filled out for all combinations, true, 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 false, false, true, and false, false. And see if we can evaluate these. Why don't we go ahead and pause the video here for a moment and see if you can fill out the truth table for these values, and then look at the columns to see if any of these expressions are equivalent. So go ahead and pause and give it a shot. All set? Great. Let's go over these. So I have P or Q and P. Well, we know that the AND gets evaluated first based on the order of our logical operators. So Q and P, true and true, or true. Well, that's going to be true. And then Q and P is going to be false, or P, which is true, so that's going to be true. Q and P here is going to be false, or P, which is false, so false or false still gives me false. And then when they're all false, false and false or false is going to be false. So true, true, false, false. Here, when they're all ORs, P or Q or P, I get these values. I get true, true, true. The only time when it evaluates to false is if they're all false. Otherwise, there was at least one value in here that I could use as a true. And then this one, P and Q or P or Q. And I'm going to do the or first because that's in the parentheses. So P or Q, which is true, and P is true. And P or Q and P is going to be true. And the last two values are going to be false, because P or Q is false or true is going to be true, but then and with P, which is false, that's going to be false. And when they're all false, it's false as well. So are any of these equivalent? Well, if you look at those two columns, they're both having the same values in every single item in the table here. So these are two equivalent expressions. In fact, you may have noticed that they're the same as the P values in the P column. So really, all of these expressions can be simplified to just whatever P happens to be in this case. And we've been using the truth tables here to verify that. So these expressions are all equivalent. P is the same as saying P or Q and P, no matter what Q and P happen to be. And it's the same as P and P or Q, no matter what P and Q happen to be. All of these are equivalent Boolean expressions. Let's try one more. How about this? If we have these two Boolean variables x and y, which of the following expressions is equivalent to this expression, x and not y? Go ahead and pause and take this multiple choice question to see which one of these is equivalent to that expression. Ready? Let's see what your answer is. The correct answer is C. Now, how could we have done this? Well, we could have done a truth table and looked at all different combinations of x and y and even these expressions. But a simpler way is if you look at C, this sets up like a De Morgan's law problem. If I distribute the not and I change the or to an and, not x is x. Or becomes an and, not y, well, it just becomes not y. So this, using De Morgan's law, gives us x and not y. So the answer is C. Hope you did well. So what should we take away from this? Over this whole topic, we've been talking about comparing and contrasting equivalent Boolean expressions. We've used De Morgan's laws to apply to Boolean expressions. We looked at truth tables to prove our different Boolean identities and equivalent Boolean expressions. And we've seen that equivalent Boolean expressions will evaluate to the same value in all cases. That's it for us here. Thank you so much for joining us at AP Daily today, and we'll see you next time. Take care.